Hello. Hey, everyone.
Hello.
Kaitlyn, Leon. Let me see if we got all of our speakers here. I think we do. Kaitlyn, Leon, Anika, Neel. Okay, cool. What we're going to do is go ahead and start. Everyone is going to have, let me see how much time we have to speak here. Basically 10 minutes. I'll let y'all know when you have 2 minutes left. If you need to wrap up the presentation, I'll send you a message and I'll turn my camera on. But otherwise, we're going to go ahead and just jump right into it. I'll also leave a little bit of time at the end of each talk for the audience to ask any questions. I might ask a few questions myself. And by the way, my name is Blake. I'm a designer at Polygent. So you might have noticed some changes coming to the web app and the mobile app. We're revamping all of that and improving the quality of all that. And we're also adding new features. But my background is in design, but also computer science. I have a PhD in computer science from Texas A&M. And so I'm really excited to see everyone's projects and what you guys have been working on. So with that said, let's go ahead and start with our first speaker, who is Neel. So what I'll do is, Neel, I'm going to add you to the spotlight here. And you can go ahead and present your project. So let me see. There you go.
Okay, let me share my screen. Is it working?
Yes, it is.
Okay, welcome to my project, analyzing the effects of Parkinson's disease on resting state network functional connectivity using fMRI and oscillating bowl time courses. My name is Neel Kondapalli. My mentor was Kaitlyn. Hope you enjoy. So let's start with what is Parkinson's disease. PD is a neurodegenerative condition similar to Alzheimer's that causes changes in motor and cognitive functions. Risk of developing the disease increases over time. As of 2020, there were an estimated 9.4 million cases of PD worldwide. And so the causes are the loss of dopamine in the brain. Dopamine is a neurotransmitter that's responsible for coordinating our motor movements. And Parkinson's disease is the result of the breakdown of dopaminergic neurons in the substantia nigra pars compacta, which is the part of the brain responsible for producing dopamine. And the resulting loss of this dopaminergic function causes the breakdown of brain networks responsible for cognitive and motor processes, which leads to a lot of the cognitive and motor impairments that Parkinson's disease patients often have. The current treatment for Parkinson's disease, which is not the most effective, is called dopamine replacement therapy, DRT. It uses dopaminergic medications to supply the brain with lost dopamine. However, the problem with this is that DRT can cause certain patients to develop LID, which causes involuntary movements and may become progressive in some cases. The current methods of diagnosis. The current diagnosis of PD is, excuse me, is based on clinical examinations and patient history. Monitoring changes in motor function can indicate fluctuations in dopamine supply, correlating with PD. Problem with this is that the current frontier of PD research is focused on premotor detection of the disease, because the longer it takes to detect the disease and later DRT is administered, the more the likelihood that the disease won't be cured increases. So current research is invested in finding earlier ways of diagnosing the disease. And the solution to this is neuroimaging. Modalities such as fMRI, functional magnetic resonance imaging, proven useful in revealing new patterns in the pathophysiology of PD and many diseases in general, which helps by revealing changes in systems affected by the disorder and guiding courses of treatment. So fMRI is a modality of MRI, magnetic resonance imaging, which uses magnetic waves to map the brain. It reveals brain activity by monitoring changes in the blood oxygen level dependent signal, or the BOLD signal. The theory is that it's called a hemodynamic response. When a neuron fires in the brain, the local blood oxygen increases for a period of time. So monitoring fluctuations in BOLD signal can indicate recent neural activity in that area. Functional connectivity is established when two distinct brain regions are temporally in sync in terms of the neuronal activity. On the right, the first figure, it shows the bold time course for one region of interest, so one part of the brain. The peaks indicate neuronal activity, so that indicates that the brain fired at that point in time. And the image below that shows two time courses plotted on top of each other. You can see that the peaks and the dips roughly line up. So we'd say that these two regions are connected through time because their bold time courses are temporally coherent. They're activating and not activating at roughly the same time. So we can infer that there's some correlation between those two regions. So why is functional connectivity important? It allows us to map how the brain's various networks interact with each other. More importantly, though, monitoring changes in FC in correspondence to external symptoms like dementia or MCI, mild cognitive impairment, allows us to understand the internal changes causing these conditions. By comparing the FC measures of a control subject to those of an experimental subject, we can associate certain changes in FC signature to the development of an experimental case. By gathering the FC data from all regions of interest in the brain, we can create FC matrices that allow us to visualize connected regions. In these FC matrices, each ROI is a node, and the edge is the connectivity strength between those two regions. On the right, I use the Harvard-Oxford probabilistic atlas to show the connectivity of one volume of fMRI. And for example, you can see that the angular gyrus, which is one of the ROIs there, it's very weakly correlated with the occipital lobe. That makes sense because those two regions are in charge of completely different things. So they wouldn't have a strong connectivity. So the resting state networks, what are these? By observing functional connectivity patterns in both time courses over the years, studies have identified 6 consistent networks in the brain that are especially active in resting states. So when people are not doing anything, they're just sitting there and like with their eyes closed and sleeping. This study will focus on 3 of these networks in particular: the default mode network, the salience network, and the central executive network. These networks specifically were chosen because they regulate many important processes related to cognition and motor skills, which are what Parkinson's disease disrupts. So in theory, the presence of PD should alter functional connectivity in these regions. And more importantly, recent studies have shown that FC signatures can serve as a loose form of biomarkers for researchers to predict diseases. This was done on Alzheimer's pretty recently. And on the right, I have plotted a atlas, the YET 2011 atlas, which outlines 7 RSNs. I've applied it to a volume of one of my fMRI scans. And I've plotted all the RSNs, and the particular ones are the peach color region, which is the DMN, default mode network. The lime green is for the salience network, and the purple region is the central executive network. These networks encompass multiple regions of the brain to dictate different mental functions, but like I said, they correlate closely with what Parkinson's disease affects. Data and workflow. The data set, the fMRI, MRI images will be taken from Parkinson's Progressive Markers Initiative, or PPMI, which is a study launched in 2010 that seeks to gather an open access data set and biosample library to advance PD research. The subjects used consist of 40 subjects, 20 with PD, 20 without. Ages vary between 50 and 70, and the visit being examined is baseline. So earlier PD, because that's the goal of this study. It's to see if FC at earlier stages can be used as a biomarker to predict the disease. Each subject has a 3D T1 weighted image. This is for anatomical reconstruction, and 2 fMRI images with different phase encodings. The pipeline, so once downloaded from the PPMI Lonnie database, subjects will be converted to comply with the BIDS format, which is the brain imaging data structure format. It improves readability, converts DICOM images to NIFTY images, yeah. And it's just important for a lot of pipelines because they require data to be in the BIDS format for input. Data will then be processed using fMRI prep, which is the famous fMRI processing pipeline used in many studies. And FC will be constructed using Nylon's high-level functionalities in tandem with Python. So the workflow. Like I said, each subject has 3 images, a T1 weighted image for reconstruction, and 2 RS fMRIs, resting state fMRI images. Each subject will be converted to comply with BIDS, and then the subjects will be run through fMRI prep without FreeSurfer because many studies have shown the FreeSurfer is unnecessary for this kind of study. And cutting server's reconstruction cuts the processing time of fMRI prep by hours, 17 hours to be exact. After pre-processed, I'll do atlas handling. So the atlas being used is the Harvard-Oxford probabilistic atlas. It outlines around 50 different ROIs encompassing different regions of the brain. The atlas will be downsampled to match the resolution of the fMRI images. This has been shown to improve time series extraction. And then I'll create a nifty masker image to overlay on the fMRI and extract the time series from all my desired ROIs. After that, covariates will be taken out. The compound regression, removing covariates is extremely important for fMRI studies because without removing artifacts or noise that can cloud the signal, the bold signal, your results would be heavily skewed and not accurate. The confounding variables being extracted are the standard white matter signal, the cerebrospinal fluid signal, and global signal. After covariates have been removed, I'll apply the masker to the clean fMRI and extract time series data from the ROIs, which I picked out beforehand based on past studies. I'll examine the bold time series to ensure accuracy and construct FC matrices and visualize using Seaborn. After that, I'll compare mean FC signatures to the CEN, SN, and DMN between PD and control subjects and perform relevant statistical analysis. And then the first 4 volumes of the confounding variables and the fMRI data are removed to stabilize the bold signal. This has been shown to improve accuracy. Model proposition. With data science utilities such as deep learning, there is a potential to create a model to extract features from FC matrices of certain regions and output a probability that a given matrix of that region correlates to Parkinson's disease or not. I have 2 models in mind to try. One is a long short-term memory model, an LSTM, is well suited towards time series data. Since both signals are time series data, constructing a model around LSTM in theory would be a valid initial approach to test. And then another approach, which is seemingly more plausible, is a graph neural network. Since FC matrices are graphs, they have nodes and edges, feeding into a graph neural network, feeding filtered FC measures, so after a threshold of around 95%, feeding that into a GNN would in theory also be a valid approach. On the right here, this is the basic architecture for an LSTM neural network, which is one of the networks I'm planning to test. Clinical significance. Research and development. Insight into how PD affects these networks in the brain opens pathways for future research into how the DMN, Salience network, and CN can be manipulated to change BD behavior. Early detection. Neuroimaging is emerging as an efficient method of early detection for conditions. It's more cost-effective, it's faster, and it's non-invasive, which is a huge plus. Knowing what to look for in scans allows for quicker diagnosis. FC signatures of these networks can serve as potential biomarkers for scientists and researchers in the future. And then model potential, either as a proof of concept or as a tool for researchers. The model developed here can serve as an FC classifier to detect potential signals of PD at earlier stages than traditional clinical methods. With more subjects in development, because 40 subjects is not enough to train an efficient model, but with more subjects as PPMI grows, the model's performance will undoubtedly grow as well. And yeah, that's it for my project. Thanks.
All right, thank you, Neel. That's very impressive. Do we have any questions from the audience or from the fellow speakers? We got time for one question, and then we got to move on to our other speakers. Anything? I'll ask a question. You know, what do you intend to do to build on this work? Do you intend to keep working on this? And
Yeah.
college?
Build on this work. What I plan to do is first, the model side of things, I plan to improve the model and test it more. But on the FC side of things, I can definitely try to expand this to either using task positive fMRI. So right now it's resting state, but using task positive can change the network dynamics. For example, the visual network and the dorsal attention network are shown to function more when you're doing specific tasks, like tapping your finger or writing an essay. So analyzing how Parkinson's affects those would be a good approach. And then just analyzing more different ROIs, performing better statistical analysis. Those are all things that, those are all possible avenues for me to take.
Awesome. Well, great work and congrats, and thank you for presenting.
Yeah, thanks.
We're going to move on to Anika. So I'm going to go ahead and make you the spotlight. And I'm going to make Neel remove spotlight. So as soon as you're ready, Anika, you can go ahead and start.
Okay, so hello, my name is Anika Pallapothu, and my project will use machine learning to diagnose coronary artery disease using adult data from blood tests and electrocardiograms. So this is a very red map of the United States. And that red, like any red, is not good, especially the darker red. The darker the red, the more cases of coronary artery disease there are. And coronary artery disease is the leading cause of heart disease and heart-related deaths in the world. Just like that statistic says, more than 18 million adults have coronary artery disease, resulting in more than 360,000 deaths in 2019 in the United States. That was back in 2019, before COVID-19. So that's 3 years later in 2022, so deaths have most likely increased. So my thesis is a machine learning model to automatically detect coronary artery disease to help keep more people alive. On the left of the slide, you can see a heart with the right and left coronary arteries. For my project, I focus on both the arteries. The coronary arteries supply all of the oxygen, nutrients, and blood to the heart. On the right of the slide, you can see an example of the buildup of plaque in the coronary arteries when the patient faces coronary artery disease, or CAD. This causes the major red blood vessels that supply the heart to become diseased, and these cholesterol-containing deposits in the patient's coronary arteries can only be found in the patient after many years. The main symptoms of CAD are chest pain or shortness of breath. Doctors can only diagnose CAD by using exercise stress tests, blood tests, or echocardiogram tests. However, these are only after the patient shows any symptoms of the disease. By this time, it can be too late for the patient to take any necessary precautions to avert the fatalities of the disease, such as stroke or heart attack. Before I get into the details of my project and of the graphs and results I got from my project, let me explain what I used. I used a 3.9 version of Python with a Jupyter notebook from the Anaconda package to code my project. I got my data from Kaggle, which consists of 303 patients. Lastly, I used 11 different parameters with one column for the results. The parameters highlighted in the red are all of the results collected from blood tests: cholesterol, fasting blood sugar or FBS, talic, and the patient's resting blood pressure. 3 parameters highlighted in dark blue are collected with electrocardiogram tests: the slope, resting electrocardiographic measurement, and ST depression. Lastly, the parameters in the gray chart are the diseases the patients in the dataset previously faced: so cardiac arrest, cerebral palsy, exercise-induced angina, and thalassemia. In this first graph, we can see that the number of normal classes is greater than the number of abnormal cases. But there's not much of an imbalance of data. If there was a greater imbalance of data, we would need to add more data to the abnormal set to balance out the data set. And we classify normal as blockage less than 50% and abnormal as blockage more than 50%. In the second graph, patients above the age of 55 have a higher chance of heart disease compared to younger patients. Here, there is an imbalance of data for the distributions of patients having the presence or absence of heart disease. In this last graph, it shows a bivariate analysis, where how some attributes correlate with the target variable, to see how different types of chest pain have an effect on heart disease. The patients who show a sign of asymptomatic chest pain have a higher probability of heart disease compared to the other signs of chest pain. This chart displays the results of different models. All the models performed well with accuracies greater than 80%. My main focus was to reduce the false negative cases. If the recall value is close to 1, then the model will never predict fewer false negative cases. The support vector machines, or SVM, had the highest recall score of 0.9, in addition to having the highest accuracy of 90%. Hence, the SVM will be the primary method of coronary artery disease prediction. In conclusion, even a regular physician can use this algorithm to diagnose a patient, especially in rural areas where there's a shortage of cardiologists. Also, instead of replacing cardiologists, this algorithm will help them to diagnose whether the patient has coronary artery disease at a faster rate with a better accuracy. Again, a support vector machine, or SVM, is a type of deep learning algorithm that performs supervised learning for classification or regression of data groups. Supervised learning is a division of machine learning that involves learning based on pairs of input and predefined outputs. Algorithms learn from patterns between input and output and optimize based on errors to correct model predictions. I can further enhance this model by using more attributes and using more of the patient's data over time to make the model more accurate. Furthermore, the model can also identify the cause of the disease so that more precautionary measures can be taken. The model can also quantify the volume of blood flow to the heart when coronary artery disease occurs. In conclusion, my project is an automatic and rapid method to detect coronary artery disease like this to help keep more people alive. Thank you for listening.
All right, great work, Anika. Do you have any questions?
I actually have a question.
Go ahead.
What was your as part of I didn't get this. What was your training testing split for the models?
It was 80-20, 80% of the data set was for training.
Thanks.
Interesting. Why did you choose 80-20 over 90-10, which is that's a pretty common convention?
80-20 I've noticed helps a little bit more with training, and it gives me more opportunity to test the data set, the algorithm, to see if the algorithm is doing what it's supposed to do.
Okay. And what was your origin story of choosing this particular, topic area?
Well, coronary artery disease is the leading cause of heart disease and deaths. And I've noticed that a lot of cardiologists have a hard time in, accurately helping all of their patients at a faster rate. So I wanted to create an algorithm that will help them treat more patients faster.
Great. So you targeting kind of the most dangerous health problem. It's kind of like go big or go home. Right.
Yeah.
Okay.
Yeah.
Cool. Great work. Let's go ahead and move on to our next speaker. Our next speaker is going to be Kaitlyn. So Kaitlyn, I will make you the spotlight. And thank you, Anika. Great work.
Okay, I'm just going to share my screen. Okay. Hi, my name is Kaitlyn Kwan. My mentor was Celine, and my project is analyzing mental health keyword trends in Reddit posts over time. So what is happening in our world right now? Recently, the CDC warned of an accelerating mental health crisis among adolescents 2 years into the COVID-19 pandemic. And the results of a CDC survey published in late March of 2022 showed that the rates of childhood mental health concerns and suicide rose steadily between 2010 and 2020. And by 2018, suicide was the second leading cause of death for youth ages 10 through 24. And in 2021, 44% of teenagers have reported having persistent feelings of sadness or hopelessness. This is why the American Academy of Pediatrics, the American Academy of Child and Adolescent Psychiatry, and the Children's Hospital Association are joining together to declare a national state of emergency in children's mental health. Additionally, recently on August 18th of 2022, Governor Gavin Newsom of California has also announced that he is coming up with a master plan to address the mental health crisis among California youth, proving that mental health is a very relevant topic. And this leads to my question that guided my research, which is what are the current most common causes or issues that are affecting mental health, especially with the big changes that are happening in our world, such as the pandemic. Some general background information in terms to know for mental health. are the three most common mental health disorders are anxiety disorders, mood disorders, and depression. And the leading causes are childhood trauma or abuse, socioeconomic disadvantages, bullying, and severe or long-term stress. So the methods that I used in my research are downloading data from pushshift.io, which was my data set that I used. I used Python, and I sorted through the subreddits and stop words, and then I used TF-IDF, which is a natural language processing tool to compare words between subreddits. And so I'm going to elaborate on all of that right now. So first, I obtained data, and I downloaded my data from PushShift, which is a social media data collection and archiving platform, and the photo of it is on the slide that, there below. And basically every file had a bunch of different posts from Reddit and a bunch of subreddits. And I decompressed the code from Z standard since it was in ZST format. And Z standard is just a compression algorithm because there was so much data. And then I had to decompress that for readability because the data is not, you can't really read it when it's in Z standard format. And then I had to organize that data. So I chose to organize it in JSON libraries. And one JSON line was one post, and every line had the subreddit name and the post content, as well as some other information about the post, but it was irrelevant for my research. And then I sorted them by mental health related subreddits so that I could isolate which subreddits I wanted to look at. And in that data set that I had, the mental health related subreddits were suicide watch, depression, health, and happy. And there were over 270 non-mental health related subreddits that I used as well. And some of those include law, business, comics, conspiracy, evolution, and many more. So next, what I wanted to do was find the most common words with the highest frequencies that show up in the mental health related subreddits. So I did this by storing all of the, by going through all of the posts in the mental health related subreddits and storing them in a variable called accumulated text. And then I used the collections counter and most common Python functions to sort through the posts and get the top 30 most common words, or the 30 words with the highest frequency. And then I did find that when I was doing that in the first round I did that, there was a lot of stop words, which are filler words like the as, and those didn't have that much meaning and weren't really significant. So I did choose to filter those out using just a list that I downloaded from online, and I turned that into a file and used that to filter out the stop words. However, one thing I did find was even with the list of stop words and filtering out those stop words, there were still stop words that were showing up in the top 30 words. And I did find that at first I was just adding those to my list so that they would not show up in the next round. But I did find that I can't really dictate whether or not a word was meaningful or significant or not. So I used TF-IDF to kind of do that for me. And before I get into what that is, these are just the results, and these are the 30 most common words that showed up in the mental health related subreddits that I was analyzing. And as you can see, the word is on the left and the frequency of the word is on the right. And the most frequent word that showed up was just. And that is just an example of a word that can be a stop word, but just has a double meaning. It can either be a stop word or it can mean like fair and like justified. So that is why I needed a TF-IDF. So TF-IDF stands for term frequency inverse document frequency, and it is a tool that quantifies the importance or relevance of string representations in a document amongst a collection of documents. So I did this by turning all subreddits. I first grouped all of the posts into their subreddits, and then I turned those subreddits into files. And then I used those top 30 words that I found previously to create trigrams and bigrams for more meaningful data. And trigrams or bigrams are just phrases with 3 or 2 words in them. And I've created those trigrams and bigrams by going through every single word in the list of top 30 words. I put it through my algorithm, and it found every single place amongst all of the subreddits, mental health and non-mental health related, and generated the phrases that that word is in, so that I could compare the phrases amongst the different subreddits instead of just words, because words don't tell me as much as phrases would. And then I displayed the frequency of those trigrams and bigrams in the subreddits in a CSV file for every single word. So that was 30 files in total. And here's just an example of what that file would look like. This is using the word depression. And on the top are the trigrams and bigrams. And on the left are all the different subreddits, but this is just a snippet of one file. The subreddits span over 270 different subreddits, and the trigrams and bigrams, there's over 140 columns of those. And as you can see, there's a lot of zeros in this file, which means that those trigrams and bigrams do not show up in any of the subreddits if there is a zero there. But as you can see in the subreddit offbeat, chance, suffering, depression showed up because it's a number that's higher than 0. And what that means is depression is not just a word that shows up in mental health related subreddits, because offbeat is not a mental health related subreddit. So that tells me that the word depression, it is not just, it's not like purely significant to mental health related subreddits, because it is showing up in other subreddits as well. So during my research, I did encounter some challenges. So the first challenge I encountered was when I was downloading the data, it was in Z standard format, which I did talk about earlier, but the data was super compressed. It was unreadable. And I had to figure out how to turn it into JSON libraries, which was my choice of formatting. And my solution was researching what Z standard was, because I was unfamiliar with it. And then I just used the ZST decompressor to decompress that. And then the second challenge was, after filtering out the stop words from my top 30 words list, I still saw some stop words in my top 30 words. And the solution I took on was, at first, I just added the stop words that I saw coming up into my stop words file so that it would just be filtered out the next time I ran the code. But I did realize that I do kind of want to leave some of the stop words in there to see how significant they were to the mental health related subreddits, and see if they are like pretty important and if they are showing up in other subreddits as well. Which leads into my third challenge, which is TF-IDF kind of acted as a second filter for those the top 30 common words. And originally I only found the top 10 most common words, but I found that when I leave the stop words in those top 10 common words, after TF-IDF proves that those stop words are insignificant, then I'm only left with a couple of words that are significant for mental health. So I expanded my the amount of common words that I was finding to 30, so that after those stop words are proven as insignificant by TF-IDF, I would still have enough significant words left over to analyze. So in the future, I'm currently trying to work on an algorithm to interpret those TF-IDF results, because there are a lot of data. I have over 30 files with over 150 trigrams and bigrams in each file, and over 285 subreddits in every file. So I'm still working on interpreting those results, which leads to determining which words at the top 30 are significant to mental health, and determining some common causes amongst those mental health related subreddits, and trying to narrow it down. And then I hope to repeat this same process with different data sets of subreddits, because the data set that I did download only had about 5 mental health related subreddits in it. So I do want to download some other data sets to test this out and see how the different, the most common words differ amongst those different data sets. And then I hope to compare the frequency of those top 30 words to events in our world, and just see whether or not those the frequency of the top 30 words change as different world events happen, such as natural disasters or like the pandemic that we just experienced. Thank you so much for listening.
All right, Kaitlyn, that was super fascinating. I have a couple of questions, and I, encourage the audience to also ask them. Why did you choose 30 stop words? Seems like an arbitrary number. Why 30?
Well, they weren't stop words. They were just like the words with the highest frequency amongst all the mental health related subreddits. And I just chose 30 because at first I just wanted to see 10, but I realized that because there's stop words that are showing up in those top 10 most frequent words, I expanded it to 20, but there was also a lot of stop words in there. So I just wanted to expand it to 30 so that there was enough room for both stop words and words that were significant. So I just choosing 30, it's not really, there wasn't a specific reason for like why 30, but I was just because I was expanding the amount of words that I was trying to find.
Got you. I meant 30 words, not 30 stop words. But another question I have, so you have these bigrams and these trigrams, you have this big list of them, 150. So, how are you thinking about further analyzing that or seeing patterns in that?
So I want to isolate the subreddits with the that did have the trigrams and bigrams show up in them. And they also have like different frequencies and stuff. So I kind of want to analyze that as well and see if there's a common pattern between what subreddits those trigrams and bigrams are showing up in. And also just trying to see if they are significant to mental health related subreddits or not. So yeah.
Interesting. I feel like it could be a situation where you could combine this work with qualitative research. Like you have all of this isolated qualitative data. You could use something like grounded theory to group these little phrases and so forth into kind of groupings. And some of these ones are like alcohol related, and some of these ones are, so and so forth. And so maybe you could start to see patterns in that way as well. And maybe you could even think of an algorithm that does that.
Yeah.
Like a clustering algorithm, essentially. Cool. This is great work. Any other questions? Okay, let's move on. We've got 15 minutes left in the session. I'm going to go ahead and pass it over to Leon. So thank you, Kaitlyn. All right, Leon, you're ready to go whenever you're ready.
Yeah. Can everyone see my screen?
Yes.
Great. Okay.
Oh, this is right to my heart. This is very related to what I worked on in grad school. Cool.
So my project is Sketch Search, and my mentor is Chris. I'm Leon. And Sketch Search is an AI-powered image-to-image search engine using user doodles, and it's a web app that's posted online. And I think I'll start off with a demo. So let me share. Switch it. So here's what the web app looks like, and it's currently live on sketchsearch.ml, and then this is just URL forwarding to this. And it lets you draw, and it'll predict in real time and return a search, as well as the next 4 top predictions. So it gives you a top 5 that you can scroll through, and you can draw different things. And even if it doesn't get it right on the first time, you can scroll through and find it. And yeah, there's a lot of different classes that are put into this, and it can tell the difference between some visually similar things, like a chair or like a bench. Yeah. So that's what the app looks like. And now I'll go into how it's made. So for the website part, the front end is built with HTML, CSS, and JavaScript. These static assets are served by Nginx, and the JavaScript is responsible for the canvas that I was drawing on, and it also is the part that sends requests to the backend in the form of a GET request that passes the base64 image data, which is decoded by Python's image processing libraries. I specifically used PIL, which is Python's imaging library, and I used TensorFlow for the actual machine learning model. So the website, the backend is using a convolutional neural network that's been trained on data that I'll go into later, but it's using the QuickDraw dataset. And for the processing that goes in before that, it downscales images and uses anti-aliasing, and then it rescales pixel values from 0 to 255 to 0 to 1. And the reason for this is the dataset that I'm using is in a much smaller scale, which lets me have better training time for resolution, and it's probably better for encoding as well. And 0 to 255 to 0 to 1 is because for training, it's been shown that rescaling values is better for having the model converge faster. And then afterwards, the convolutional neural network predicts, and it returns JSON in the request that contains the top 5 predictions. And in the front end, that is processed using an iframe, which shows search results from me. And so for the prediction pipeline, the user draws an object and there's a convolutional neural network, and it classifies the sketch, and that's sent back to the front end. So I'd like to go into the model now, and I'm going to talk a little bit about convolution. So convolution is sort of this process that's shown on the right side, where you can see this shaded matrix that's sliding over the image. This matrix is called a kernel, and each of these values has a specific weight, and these are multiplied element-wise and then summed up to produce a final image. And this is like the process of encoding that's done multiple times through multiple layers, and also within layers multiple times. And that's shown on the left side. So this is sort of the structure of a convolutional neural network, where you have the input and then a convolutional layer that's made up of multiple of these kernels and their feature map outputs, which is what is after the multiplication. And you can see there's 6, and some of these might extract edges. In a more general sense, these earlier layers tend to find the more high level and not class specific characteristics such as edges, but as you go deeper into the network where these are passed through more convolutional neural networks or layers, it gets more specific to class, and it becomes less comprehensible for people. And then eventually, these are 2D images, but it's flattened out into a dense layer that's one-dimensional, and finally it put into an output layer. And the dense layer is similar to the convolutional layers, but instead of a kernel, it just has a single weight for all of these individual pixels that become neuron activation values. And the final layer is composed of the number of classes, and the value of each neuron corresponds to the confidence it has in that specific class prediction. And in this example, it's using digits, but for mine, it would be using the doodle and into a classification. And for the actual specific architecture of my model, it's this, and it starts with the input and has 96 11 by 11 kernels. So 96 of those sliding kernels in the first layer, then 256 5 by 5, 384 3 by 3, 384 3 by 3, and then 256 3 by 3. And then finally, this all of these are flattened out into a 4096 dense layer where it becomes one-dimensional neurons. and then again into another 4096 dense layer, and then into the final prediction. And this size is the correspondence to the number of classes, which I'll go into. So for the data set, I used QuickDraw bitmaps. And QuickDraw is an open source Google project that it contains 50 million drawings across 345 categories and is contributed by players of the game QuickDraw, which is a Google game where you draw pictures until their AI recognizes them. And so I took 100 classes for 1,000 images each in my initial test of this, and it uses 28 by 28 bitmaps, which are just each pixels corresponds to a pixel value, and it looks like this. Or actually, this right side image is directly from the data set. And 341 classes with 5,000 images each is for my final model, where I have 4 classes taken out, I think, for the proper nouns, like the Great Wall or some, I think might have been the Eiffel Tower, but those are not like general objects, so I removed them. And I also increased the number of images I used once I found out 1,000 did okay. So for the training procedure, I used 100 epochs and 256 batch size. In short, like in each epoch, the model can readjust those weights in the kernel and also for each neuron in the dense layers to improve its loss. And so loss is the way the model evaluates how poor the predictions are or how bad it is after going through like one epoch of looking at training data. And for the batch size, this is just the subset of the training images used that are actually used to adjust the model values, because not all of them will have an impact on the weight. And part of this is one for increased training speed using a smaller batch size. And another benefit is that there's a sort of a degree of randomness where it can not use all of the images. And this allows it to avoid minimums where it's not the absolute minimum. In this image on the right, it's actually like there's only one variable, but in reality, with all of those weights, this is actually like very multidimensional, and there can be a lot of minimums that are not the actual minimum of the cost function. And ideally, you want to find the lowest possible loss for your model. And for my results, I got 100 classes for 1,000 images, 100 epochs. For that, I got 86% accuracy. For 341 classes, I got 70% accuracy. And for a model that has this many classes, it actually performs pretty well. Even though like the number of classes triples, it maintains 70% accuracy. And for some of the broader purposes of this project, beyond the just being interesting, I think the image to search pipeline is something that can be applied in replacement of something like Google Lens. Because the way Google Lens works right now is that it finds visually similar images. So if I were to plug in a doodle, it would give me a similar doodle, but sometimes that's not what you want. Like you want the actual object itself. And in some cases, like foraging, it's important not to just go by visually similar. And Google's, I believe, AI solution is general, and for that reason, it sacrifices specificity. And in cases like foraging, it could be life or death. And so having a specific model that's trained for classifying in that and not just finding visually similar images can make the difference in what is effective for that specific application. And another potential avenue for this pipeline could be for medicine recognition, where finding visually similar things is not necessarily a good idea because there's some mistakes, and also having that level of specificity is important for being able to recognize that specific like medicine. And that can let people retrieve stuff like dosage or side effects or all the information needed, especially if they've lost a label or something like that. I can see a lot of potential in this pipeline for a wide variety of applications. Yeah.
Awesome. Very fascinating work. Thank you, Leon. This data set is one I'm very familiar with, the Google Quick Draw data set. One of my questions for you is, why did you choose the kind of compressed bitmap data versus the raw data, which is vector data of the sketch?
Yeah. I think one reason is because this is more of a proof of concept for a larger image to search pipeline, as I was talking about before, for like say foraging. The other thing is, I believe this data is easier to process, whereas if you use the, I think, time scale data, where it gives you time as well and the individual strokes, you would need to use an RNN, and that's not as like applicable to certain things. Sure. Yeah, bitmaps are just more like compressed, and for the web app's sake, it's less data that you have to send through if you just send an image versus if you send all the strokes and the time, and it is lower resolution for that matter too.
Makes sense. And when you trained your classifier, it looked like you chose 5,000 drawings total.
Yeah.
What was your reason for that particular number?
It was more for the sake of training time. I did increase it from my initial test of 100 images because there's more classes. So with the variety of drawings and different like interpretation of certain objects, you need sort of variety. I sort of just, it's a little bit arbitrary, but I think from 1,000, I found that it was 1,000 could miss certain cases just through like my actual drawing. Yeah, I don't have like empirical for how good it is, but I noticed that between the 1,000 image and 5,000 image, when I drew certain things, like for say like a chair, if I drew it in 3D, sometimes the 1,000 image could miss it, but 5,000 images seem to catch like different interpretations of a drawing more.
Got you. Makes sense. Awesome. Any other questions from our fellow speakers or audience members? What was the training time for those 5,000 drawings?
I'm not sure in specific, and this will also vary based on like what you're using, I guess. For I'm currently using Google Colab as my method of training things, and I have Colab Pro, I believe. So my training time probably varies from people who just use it normally. I think it was over several hours, and it also depends on the model complexity. I initially had a different model, actually. Yeah.
Got you. And can you elaborate a little more when you mentioned your example of kind of applications of this work? You mentioned foraging. Could you elaborate a little more on like kind of specifically what you mean by that? Like what's an example of foraging and how this could be useful?
Yeah, so there's actually a video on YouTube by a channel called Atomic Shrimp that tests apps that are specifically dedicated to foraging. And then it also tests the capacity of Google Lens and its ability to detect, like, I think it's plants in particular, detecting between certain commonly confused species that can be either edible or fatal based on.
Got you.
So I think one specific example that Google failed on was between hogwort and hemlock, and one of those is very lethal. So it is definitely a mistake that is not like affordable, and it's probably due to the nature of Google Lens being something that tries to find you. It's a general algorithm for finding visually similar images, but not necessarily suited for certain applications of classification.
Got you. All right. Any more questions before we end this session? I don't think so. Well, I want to thank all the speakers. This is fantastic work and truly amazing work, honestly. I mean, I'm really looking forward to seeing how y'all develop and the kind of work you'll continue to do. This is very advanced stuff. I mean, some of this stuff is very like graduate level computer science. So awesome work and congrats on your projects. And I wish you all the best in the future. So thanks for presenting.
Thanks.
Thank you for hosting.
Thank you.
Take care, everyone. Enjoy the rest of the symposium.
Take care.